Uh, Guys, download the notebook from this link and upload it in, maybe locally you can run it, or perhaps in Collab. Okay. Let me know if anyone faces any issue in opening the notebook. Then we will start. Okay, so we can start now. So in this tutorial, we will be mainly focusing on node classification and link prediction task, as Sir previously stated in the previous lecture. So we will be using one of the common package to write this GNNs and all, that is PyTorch geometric. So you know PyTorch has been used for this machine learning models. Now PyTorch geometric is specifically for graph neural networks, right? Okay. So what are the goals? We will understand the basics of GNN. How do we use PyTorch geometric to handle these graph structures? We will train a GNN model for node prediction, node classification, link prediction, and meanwhile we will discuss some points, ask questions, etc. Okay. So yeah, water graphs, as already discussed, you know. You also know what are some examples of the graph. You know what are graph neural networks and why they are used. So I'm not going into those. Yeah. So PyTorch geometric, why PyTorch geometric? PyTorch geometric, basically it helps to handle the graph data structure pretty well. It has already like CNNs, this linear transformation layers, etc. This PyTorch geometric has already this GNN layers. So you have to write the GNN layers from scratch. You can just, so whatever functions you were looking at, right? Those attention layer or like the graph sage, GCN already have been defined. You can just use in your machine learning pipeline. They also have some data sets, so you don't need to download data sets or create data sets, although you can using PyTorch geometric, but you don't need to. There are very standard data sets already existing for variety of tasks. Okay. And they also have some tools to tweak with this graph. Okay. So before starting, you need to install some necessary libraries. So these are some of the packages you can go and install. I guess some of the packages won't be available in Collab. So just go and install this and let me know whether it's done, because it takes a little bit amount of time to install. Let me know if someone's installation has been done. Done? Okay. So first we will import some libraries. These are standard libraries. You will mostly see this torch geometric being called again and again with this GCN conv, sage conv, gat conv, which are the common convolution layers which were described earlier. Okay. So this is just a standard function to just print some data set, and it just shows what is PyTorch version, what device you are using, etc. Okay. So yeah, you can also change to GPU if you want faster computation, but CPU is also fine, not a problem. Okay. So a graph in PyTorch geometric is represented as data, this capital DATA, data objects, right? So what this graph data object generally holds? X as in the node features. So previously we were discussing that at 0th or the H0 being the first node features, that is X. So you can find the dimension of this node feature is basically the number of nodes comma number of features, right? Then there is edge index. So generally what we do is that we don't the identity matrix, because identity matrix can be huge, right? So let's suppose you have, let's suppose 1 million nodes, but you have, let's suppose 10 edges. So why will you store a 1 million by 1 million identity matrix? It's better to have a very small set of edges in a very compact manner. So that's basically 2 comma number of edges. So 2 representing the pairs, so u comma v, right? And y being a node level or a graph level. So let's suppose if you have a node level task, like you want to classify nodes. So y, the dimension of y will be some number of nodes comma number of class. If it is a regression, can be number of nodes comma number of targets. Let's suppose it has multiple targets. If it's a graph level task, then it will be just one value. Okay. Yeah. So how do we create a simple graph, right, in this PyTorch geometry? So let's suppose we want to create a graph with 3 nodes and 2 edges. So nodes being 0, 1 and 2, right? And edges being, let's suppose from 0 to 1 there is an edge, and 1 to 2 there is an edge, right? So it's a directed graph. So at first, in line number 5, you will see we will create a tensor of node features. So basically for each node, for node 0 in line 6, you have, it has a feature minus 1 comma 1. Node 1 has a feature 0 comma 0, node 2 has 1 comma minus 1. So basically the node, each node has a 2-dimensional feature. And I draw 2 edges, basically from 0 to 1 and 1 to 2, right? Okay. Now we create the data in this manner. Basically, as already we have imported this data class, we create an object of it. We pass this X as a feature of the nodes and edge index, right? And it just prints the data. So this is a graph. So what other attributes can you have in the graph? You can have multiple attributes. As discussed earlier, you can have attributes for its edges. You can have some extra node information. Let's suppose you want to keep some node to be true, some node false, as a, like, let's suppose you want some nodes to be a training node, some nodes to be something like that. So you can also create a tensor, keeping the dimension same, and assign. So we already created the simple data, right, in the previous cell. So we just assign this new information in this manner, and if you print it, you will find that this new information has already been assigned. Okay. So these are just some functions to just look at the graph. We will see now. Yes. So we just plotted the graph. So as you can see, there were 3 nodes, there were 2 edges. So it was a directed graph. From 0 to 1 there was an edge, and from 1 to 2 there was an edge. And you can see the features of the nodes, right? So now you understood how we created a graph, how we features to how we created the edges, etc., etc. Okay. Where? Okay. Here. So node info is basically, I just created an attribute for each node myself. It need not to have node info written. You can have anything written, right? It's just my way of writing that it's some information of the nodes. You can have node attr, something like that. It's your way of writing, right? Okay. Yes. So, yeah, now some discussion point. What are some other attributes that you can assign to this graph? So, some examples being train mass, test mass. What other attributes do you think you can assign to the graph? Just anyone can answer. There are some nodes, there are some edges. What do you think you can assign, or what particular property do you think you can assign to a graph which you can, like we were storing node attributes, some edge attributes, you can keep these attributes in this data object. Neighbors are label, yes. So y is the label. So in the earlier cell you saw it has x, edge index, and y. Y is a label. Other than these three standard things. Yes, degree you can keep, but generally is degree can be computed. So it's now the thing, do you want to waste time to compute degree or whether you want to waste space in storing degree? Okay, so let's just see what we can store. These are just some of the examples. It's not exhaustive. So you can have some masks being which nodes are train nodes, which nodes are validation, test. You can have positions, right? So like we were discussing that we can have positions of each node. Let's suppose in previous talks by Professor Shanmuga sir, you saw that nodes were located in 3D space, right? So each node had a three-dimensional position. You can possibly store that, right? You can have edge attributes, you can have batch, right? Okay. So val mask is like, we will come into the experiment part. So given a graph, you have, let's suppose 1000 nodes. Out of those 1000 nodes, you want to keep, let's suppose 100 nodes to be train nodes, 500 nodes to be validation nodes, and the rest to be, let's suppose, test. The connections is there. Just you are stating, so it's basically a Boolean vector where it states that which nodes are validation and which nodes are not. Yes, yes. So yeah, when you are training, the model will get information of the validation nodes. The model will get information of the test nodes also, but it won't be backpropagating on the prediction on those nodes. Right. So we will come into that. Right. Yes, yes. Ideally, in other classical machine learning algorithms like this image and all, where so in graph level task we don't have it's not a leakage, but in the node level task, I know it looks like a leakage, but it's not. But it's basically like you have the node with you, you just don't know what the node class is or the value associated with the node is, right? You just know some of the nodes and you want to predict the value for them. Yes. So yeah, the labels will be there. So, but for the back propagation, so what happens is that when you calculate the loss, right? You calculate the loss for a train set, right? So this mask will just help me to backpropagate on the predictions on those nodes only, which are train sets. I will save the model based on the prediction on the validation sets, right? So it's basically just to keep a check that I'm not training on a node and also keeping it as a validation, right? Okay, so there's a coding point. So you guys have to write code, obviously. Create a graph of 10 nodes, at least 15 edges. It's a directed graph, so you can have any directions as you want. Assign random features of dimension 5 to each nodes. Assign edge weights. assign some class, so binary class, so 0, 1 to each nodes, create a train test validation mask. Yeah, obviously, if you add all this mask, it should all be true, 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 true. Sorry, or yeah. So there shouldn't be any overlap. And you already, there is a function draw graph with attributes. Use this function to plot the graph. Just, I'm giving you around 5 minutes. Just see what you can do. Once, so that I can proceed. Random being, you can use random package to assign these things. You can assign by your own. It's just look at the above cells, how I have assigned, and just do it accordingly. So for the edge, to add the edge, it's, you can see the dimension is 2 comma number of edges, right? So the what does 2 means? Basically, it's like 2 number of edges tensor. So first row is basically the source nodes. Second row is target nodes. Oh, so yeah, 5 minutes are over. Let me go to my implementation. Obviously, implementation can be different. So yeah, I just use torch.rand to assign some features and all. So as you can see, I have 10 nodes with 5-dimensional features. I have 15 edges. Each edge has an attribute. So since there are 15 edges, 15,1 as an attribute. You can have high dimensional attribute. Each node has a binary class. These are 10, but if you print it by separately, that they are not over. Graph, you can see that somewhat of a structure. I have assigned the edges randomly, so obviously it can happen that a node is left out. But yeah, this is a graph. Notice that there are some directed edges and all. So yeah, how do you modify the previously created graph to make it undirected? Right. So that is also a coding point. What do you suggest to do? What are you? Yeah. Just check whether the reverse one is existing or not. If not, just add it. That is ideally the case, but why just do if you have built-in package? So just built-in function, just it creates the edges that are not existing. So yeah, it increases the number of edges. And if I print it now, and it's basically a connected, it's basically undirected graph. So you can see the arrows are on both sides. Right. So now we understood how do we create a graph, what are the attributes inside a graph we can store, etc. etc. Okay. So now we come to node classification tasks. Right. So what is the task? We have to predict a category or a label for each node in the graph. So in this example, I have used a citation network where each node represents a research paper in different academic fields, and I have to, and there are connections among them, let's suppose as per citations, etc., etc. And the features of each node is the, let's suppose the content of the paper in the text embedding. So yeah, so the Quora data set has these features, these attributes: nodes, edges, node features, and labels. So you can get the data set from this data sets planetoid. This is how you load the data set. So you have, you just call this planetoid class to create this data set. And you can see, I have just printed some of the properties of the data sets, and you can see the number of graph is 1. So in this data set, you have only one graph, the number of nodes, number of edges, features, etc., etc. So is there any doubt in this part? Or is it self-explanatory? I guess it's okay. Yeah. Moving forward. Yeah. So this is a code just to show that what does the train test validation split look like? So basically this is a graph, it's a web-like structure, and the blue ones are the test, and you can find very few nodes which are train, right? So basically, given those train nodes, you are giving this GNN, this whole graph, train, test, validation all together. But the labels of the test and validation are not known to the GNN. Only the train is known. So given this graph, given the train labels, it will try to predict the train labels, right? And based on that, we will try to see how good we can do. Yeah, so defining a GNN model, here we are taking graph convolution neural networks. A two-layer GCN can be defined as follows: a softmax of A tilde, ReLU A tilde X. So basically, this ReLU inside the part is the first layer, where you multiply the features with the adjacency matrix and the weight matrix. You pass it to the activation function, and you get the updated features. You again multiply with A, and the next weight matrix. Okay. So how do you? So yeah, this is a just pictorial view. So given A and X0, you pass it through a GNN layer. You then pass it through a ReLU. You get X1. GNN, you again send the same adjacency matrix, obviously, and because it looks for the neighborhoods, right? And updated features you send to the GNN. Define the same thing that was drawn here. What did we do? Is that we create a class. It's GNN 2 layers. So first, this is the first GNN layer, where in channels is basically the number of node features that we had. Initially, when you created the graph that manually you created, it was 2. Here, the features in the previous cell, I guess you can see, it was 1, 4, 3, 3, right? Yeah. So in channel is that. Hidden channel is basically what you keep in a standard MLP, right? So the number of hidden channels. Second convolution layer is basically the hidden channels, and out channels is basically, if it's a classification task, the number of class. If it's a regression task, let's suppose it's 1, etc. So how do you do that? There's basically convolution 1, you call it, you pass the X, the edge index, pass it to the ReLU, drop out. It's optional, you can keep, you cannot keep, it's just an optional thing. Then you again send it to the next layer, and then you send it to the softmax. Literally what we have shown in the diagram. Is there any doubt? Other than the dropout, does it look similar? What we have drawn and what we have coded? Okay. So now, since we have written a code to write 2-layer GNN, what if we have n layer of GNN? Just we cannot keep adding con 1, con 2, con 3, con 4 like that. We have some smart way to have n layers of GNNs, right? So just write a new class. This is GCN n layers, where you can take n layer of convolution layers and keeping the same hidden channels, input channels, out channels. And like previously, you were not taking the number of layers in this class initialization. Here you can take the number of layers, obviously. So just 2 minutes, just copy paste the above and modify what you have to do. I guess in CNNs you have already done that. Basically just think of some analogous version of graph. Done? Okay. I don't know whether it will be same. It's basically, the diagram is something like this. So it's my implementation. You can have different. I just kept some checks, something like that. And yeah, I used some module lists to keep. Yeah, so let me just run this. Okay. Yeah, so we have defined the model. Now we will go to training the model. So I have defined 2 functions just to train them. Right? It's basically just simple. It will pass it to the model. It will get an output. It will pass it to the loss function criterion, etc., etc., and it will do the backpropagation. And in case of testing, it will calculate, since it's a classification task, it will do some accuracy calculation. Yeah. So here you define the GNN model. So here you pass on the number of in channels, hidden channels, out channel, just optimizer criterion. Yeah, you pass the data to the device. Yeah, these are just some of the lists that are necessary. You print the model and you get something like this. Okay. Now in this loop you train. Just a standard ML training protocol. Just call the train function where you send the model, criterion, and the optimizer. It trains, returns the loss, validation same, etc. So if you run this, okay. So this next cell is basically plotting. So you can see how the validation accuracy increases, gets saturated at one point, how the training loss decreases. So how do you, so yeah, now you save the model based on looking at the validation. That's, you don't know what the test was. So like you do in other machine learning pipeline. So you save the best model looking at the validation set. You loaded the model and you got around 81% accuracy, not bad. For a 7 class prediction, not bad. Okay. So yeah, how will it look? So you saw that PSNE plot of the graph, right? Before it was trained. How will it look? What do you think? How will it look after training? How will the node embeddings of each node look? Can you guess? Have you trained decision trees? Anyone? How does it look? You can partition the samples, right? Using some decision boundary. Here also it will look somewhat similar. You can see, sorry, my mistake. You can see how the nodes will be separated from each other, since we are getting 81% accuracy. So you can fairly figure out some decision boundary. So like the orange can be segregated out, the greens can be segregated out, right? So you can get a fairly good decision boundary. So initially it was like this, it was all jumbled. Now after passing through 2 GNN layers, you get this, right? Okay. Yeah. So how can we improve this model? So we already got 81% accuracy. How do we think we can improve the model? Any suggestions? Yes? Yes, more layers, right. Any other? So you saw that we use GCN, right? In the previous talk, we saw that there are other models like GAT, GraphSage, GIN. You can also use those. Yeah. And there are also feature engineering, some complex architectures, jumping knowledge, etc. So what are the common pitfalls of this GNNs? What do you think are some of the issues that this GNN still has? Yes, so it doesn't capture long range dependencies. As stated in the earlier lecture, if you have 2 layers of GNN, it will maximally capture 2 hop distance information. So if a node is very dependent on a, let's suppose, 100 hop far node, it won't be able to capture that dependency. Also, one other thing is that over smoothing. What do you think over smoothing is? And how does it happen? Yes. Node embeddings, yes, they are included. Yes, then. Right. Right. So the to capture log dependencies, what is the trivial thing? Okay, let's just use a very large number of layers. We will get capture the longer dependencies. But the issue, since you do this aggregation again and again and again, after a certain point of time, you won't be able to distinguish between two nodes. Because if, let's suppose, the neighbors are same, and you do this aggregation again and again, the features will look exactly the same. So you do an over smoothing. So yeah, this is a knowledge jumping knowledge architecture where people just concatenate each layer outputs together and then pass it through a linear transformation. You can implement it. I've already done that. It's fairly similar to the previous way, where you take the n number of layers, and here I'm just basically concatenating at line number 22, right? So at each layer I'm concatenating and then I'm passing it through a linear transformation. I defined, I created an object. Yes, now I train. So this is another training on the n layer GNN, where I took n to be 3. Right. Okay. So here I plot the training here. You can see it's fairly similar. Yeah. So yeah. Shouldn't be one layer, it should be two. Standard. Basically, right. So yeah, we got a little bit bump in accuracy. It changes obviously. Okay. So how do we handle a data set very large number of nodes? Any guesses? So if you have a way, so you saw that the large number of nodes are edges. You saw that in the previous talk, the time complexity is dependent on order of edges multiplied by the dimension d. So if the number of edges are huge, how do this is not here? Any? So as you can see that since the graph is huge, how will you predict faster? How do you do in images and all? Do you reduce it into a smaller image? Do you process a sub part of the image? What do you do? Any guess? Yes? Yes? So, going to answer here, the answer is in the next two talks. But yeah, there are some approaches to reduce the graph into a smaller graph perhaps, so that you can take lesser time to process, etc., etc. So is there any doubt on node classification task? Was everyone able to run the code? Okay. Was everyone able to define the n layer GNN? Did you compare the results with different number of layers? Just see how the results are. Do you see any performance increase? Or what if you take a very large n? Do you see any performance decrease? Okay, so I will move forward. I guess you can run the code, and I will also share this. It will be easy. So for link prediction, what do we do? So in the previous task, we were given, let's suppose, a set of nodes. We were keeping some certain set of nodes to be trained, certain sets of nodes to be validation, and certain set to test. But in link prediction, it's different. We keep edges to be trained. So here there are two types of edges. One is positive edges, one is negative edges. What do you mean by positive and negative? So let's suppose there is a connection between me and him, right? And which is not known to you. The model's task is to predict that. If it is able to predict, good. And let's suppose there is not an edge, but still the model predicts, right? So the edges which are not present, those are called negative edges here, right? The model's task is like it has to predict the edges between two nodes, it also has to know which edges are not between two nodes, right? So that's why we are keeping two different types of edges. So yeah, we run this code. So what it does is basically at each line you can see that it splits the training, it splits the data set into three parts: training data, validation, test data, right? And you can see the negative edges are quite high, as in there are lot more edges which are not present between two nodes, and the model needs to be able to predict this, that there is no edge between two nodes, right? Okay. So yeah, so you can think of it as an encoder decoder part, where as here in this diagram, the first part where you send the graph, the x and the edge index into the GNN layers, that is the encoder part. Decoder part being the rest of the part where you compare the features between two nodes and predict whether there is an edge, right? So I have defined the score function to be something like this, that is Z transpose U Z the V. You can have your own function, so you can obviously write that. So yeah, so I wrote the class in this manner. So encoder is basically two-layer GCN basically, right? And the decoder part is so this is node IEMB, this is node JEMB, and I do dot product on this and then some, right? And yeah, that is basically, so I am doing just that, just the dot product, right? Okay. So you can also have some complicated version of those where you again you concatenate the embeddings, then pass it through an MLP. You can have those. I just took a very simple approach. Okay. So here we will be using binary cross entropy loss to predict whether there is an edge or not. So a very similar training and testing function. Here we define, here we create an object. Yes. Hmm. Okay. So we have trained a model based on that. So in the so if you can just a few things. Um, in the training, you are sending the LP data X, basically the features of all the nodes, and you are sending the edge index for the train, right? You are decoding based on that, and you're calculating on the edge labels, right? Uh, so edge labels have positive and negative and all. So for test time, you are again for the encoder part, you are again sending the edge index of the train, right? So in the test setup also, you don't know whether there is an edge between two nodes or not. You are sending whatever edges you had in the train, you are sending that. And the output has to give some prediction between whether there is an edge or not between two nodes, right? So this is, and so when you are calculating mm, the loss, you are basically doing on current LP data, right? So yeah, you train on it and you print. You can see the A under curve just like that. It's a similar way of evaluating. You get around AUC of 83, not. Yeah. So, huh. Previously we generated a TSNE plot of the node classification task and compared with what if what is the TSNE plot without training it, right? Now compare the TSNE plot of the node classification task and the link prediction task. So what is the TSNE plot of the embeddings from these two different tasks, and what are observations? I'm giving you around 10 minutes. Just, I have kept the variable in such a way that it doesn't overlap, so it will be easy to do. if you want to know how to plot TSNE, get a TSNE plot, you can just go a little above and see there are some cells which are plotting. So you can use those. So what do you think the similarity, or what you can conclude from both the plots, and what you can distinguish between them? So you can see that this was the node classification task. Can segregate each class fairly well. Here also you can do it, but not as good as this, right? You can get a fairly decent accuracy, but why fairly decent? That is also a question. Why fairly decent? Because the GNN part that we were taking is, so what we were doing is that our model had a GNN layer and then just dot product of the features. Since we are just doing a dot product, there is no additional learning happening after that. Just the previous part is basically similar to the node classification task. It is somewhat similar, but the weights are learned in a way to handle the link prediction task. So although the task being different, but since the internal structure is a little bit same, hence you can maybe get a fairly good boundary, but not as good as this training for node classification task. And you can see that there are much more number of edges and all between this inter class. And also one thing, why this happens, why you can do this, because this is a homogeneous graph where there are edges between two nodes which are probably in same neighborhood or same class and all. So if you are able to predict the class of the label, you can in some way say that, okay, there is an edge between these labels. So it's like you will most probably find edge between two computer science paper rather than a computer science and maybe a humanities paper, right? So there is a high probability that you can find an edge between two same papers from same domain, right? So you can think in that manner that the edges can be predicted with high probability between similar class, right? But yeah, obviously there are other factors. Yeah. So for a homogeneous graph, it can be thought in this manner, but in a heterogeneous graph, it's not the same. Okay. So we have done for Cora. I've not written here. You can do it for the CiteSeer dataset. So you can refer to this link where you can download. So downloading is not like you have to download, upload, nothing like that. Unless and until it's your own dataset that you are creating, you can pretty much get most of the data already available written in the PyTorch package to download easily. Right. So you can use the same planetoid class to so similar to like instead of Cora, you just write CiteSeer and you will get the other data set. So that means it's in Planetoid. That's why I'm saying there are other classes also where you can get different data sets. Right. Okay. Yeah. So we understood how we can represent a graph using PyTorch geometry. We understood how we can train on GNN model on node classification task, on a link prediction task. We understood how to write or how to make different models as how information passes on from one layer to another, etc., etc. Yeah. So further, what we can do is that we can have different types of GNN layer. So in the definition of the GNN layer, GNN model, you had GCN conf. You can replace it with GATConf and see whether you get a better performance. So GATConf, what does GATConf do? Is basically you calculate that attention score, the alpha ij between two nodes ij, right? And it incorporates in the propagation function, right? So this was a node level task. There are graph level tasks. So such as sir was discussing, if you want to get some molecular properties such as, let's suppose, toxicity and any other thing associated to one graph. So here we have labels for each node. Now I have a label for each graph. So one graph has one label, right? So how will we do so? So there, as sir discussed, that we can do pooling on the node features and then pass it through linear transformation, learn it, those kind of. So there are some other data sets like TU data sets and all where you can do graph level task. Okay, so there are heterogeneous graph where nodes have different meaning, right? So in the Cora data set, what we saw is that every node is a paper, right? Now, heterogeneous graph can be thought as in the recommendation system where user and product. User is a kind of node, product is a kind of node, right? So it's a heterogeneous graph, right? So there are some scalability approach. Scalability, you can take sampling, you can do graph partition and work on partitions. Then there are other problems on graphs such as dynamic graphs where the graph structure is changing with different time. As you saw at the early part of the previous talk, as the graph cast, where the graph, if each node represents location, each node's weather changes with different time, right? So that's a dynamic graph. Transaction network is a dynamic graph. So those are the further explorations. And yeah, there are other advanced link prediction, so like knowledge graph embedding, etc., etc. So does anyone have any doubt? You can have doubts on other tasks which have not been explained. If you have any graph related problem, how do you want to incorporate, you can ask. Okay, so one quick question: how do you think uh, I can use a graph neural network on image data set? How will we do that? And how do you think graph neural network is similar to CNN? Yes. Right, right. So yeah, there you have a great kind of graph, and so basically a graph neural network is basically a universal architecture where you can use that, you can modify the adency matrix to act as a CNN. You can modify the adency matrix to act as a normal neural network. So how will you do it as a normal neural network? Just a quick thought. Let's suppose, I know using graph neural network to mimic a linear transformation is redundant, but how do you do so? Just think of the propagation function that you had. What does the propagation function do? The propagation function, if you can see that it looked through its neighbor, right? So V in the neighborhood of U. So right, no, I'm talking about yeah, you are talking about GNN to CNNs, right? Yes. So what do you define as neighbors in previous layer? No. So in a neural network, you don't have, so keeping, let's suppose it's a node level task. So nodes are samples, right? And the adency matrix does is that connection between these samples, right? So there is an information flow from one to another, right? But a neural network don't have any information flow from one sample to another. Every sample is independent of each other, right? So if you take the adency matrix to be an identity matrix, the graph neural network will mimic a feed-forward neural network. Right? So there, NU is null set. So you take this NU union U, right? So basically takes itself, and that's it. So it processes only its own information. That's it. Right? So if you take neural net, if you take adency matrix to be identity matrix, it's a feed-forward neural network. So the adency matrix, how a graph network can make a feed-forward neural network or a CNN, right? is that you guys have seen this image segmentation, object detection, etc., as a CNN task, right? How to define it as a GNN task? Can you do so? So you have an image, previous had a bounding box. Let's suppose I say you don't need to have a bounding box, you just have a segmentation, right? How do you define image segmentation using GNNs? Right. You can do node classification. So you create a grid graph and you label the nodes that you want to segment area, that I can say that, okay, there's a dog, there's a cat, or there's etc. So you can have a label for those nodes and you so there, I think you need a positional embedding also, because since position is required in CNNs, right? I guess you will need, but yeah, you can mimic that using a GNN. Okay. Okay. Is there any questions? Any doubts? If not, then yeah, the tutorial is finished. Okay. I will share this slide. I will share this notebook. So some cells were not written in your notebook. I will share this so that you can get that. Okay.